Hello, this is Mr. Stansbury. I'm going to take you through some of the problems from the 4B assignment. Start here with number 1. This graph shows the cost C of buying X bottles of juice. Find the model connecting C and X. So what we want to do is we want to find two nice points. 0, 0 is about the nicest point we can find. So let's do that. And they have this here, but I don't know that exact point. This is on a nice spot, so I'm going to use this one. So that is going to be at 2 and 5. So really it's what we want to know is, let's see, the model. So we can tell already that the y-intercept is 0, and then our slope is going to be up 5 over 2. So for A, we're going to have cost is going to equal 5 halves X, number of bottles, plus 0. Or a nicer way would write that would be maybe 2.5x, and then plus 0 doesn't have to be added on there. So I just go 2.5x. You're welcome to stick with 5 halves x, or 2.5x, whichever one you want. Okay? B is the model exact or approximate. Since all of these dots lie exactly on the line, and it should be like every bottle you buy, it should be that the bottle should be the same amount. It doesn't show that there's any kind of discount for buying extra bottles or whatever. So this should be an exact answer, because again, all these dots are exactly perfectly on that line. Okay, and then part C, can the model be used to find the exact cost of 12 bottles of juice? Yes. If so, find the cost. So cost is simply going to be 2.5 times 12. And that is going to be what? 24 plus another 6 is going to be 30 bucks to buy 12 bottles of juice. Okay? All right, moving on to number 3. A tank contains 265 liters of water. Taps left on and 11 liters escape per minute. Construct a table of values for the volume V, liters left in the tank after T minutes. Okay, so we're just going to make a quick little T chart here. So let's see, we will go T for time and V for volume. So we're going to go 0, 1, 2, 3, 4, and 5. So it starts with 265, and it's 11 liters are escaping per minute. So actually part C says find the linear model. I'm going to just, I think it's going to be easier if we, we'll save that for then. So anyway, so if we're at 0, we haven't lost anything yet, so we're 265. After 1 minute, we've lost 11, so if we subtract 11 from 265, we are at 254. Subtract 11 again, 243, and we keep subtracting 11 at a time all the way down until we get this all finished off, right? So 210, I believe, is what we should get all the way down for that. So there's our table of values. Draw the graph of V against T. So now is where we want to just sketch ourselves a little graph here. And so let's see, T is going to be this down here. So let's go 5, 4, 3, 2, and 1. Okay, so this is liters. And then this is going to be, that's not liters, that's minutes. Right, and then our liters is what we have left. So let's maybe do, say, 300, 200, 100, and we'll roughly get that in there. So we're at 0, we're at 265. At 1, we're at 254. So it's roughly there. 2, 243. 3, we're at 232. I feel my dots are a little bit too, I gotta go up a little bit farther. There we go. 3 is at 232. 4 is at 221. 5 is at 210. So that should be hopefully roughly a straight line there, right? Okay. Find the linear model connecting V and T. Can't check that off, didn't do it yet. So that is going to be this is volume in liters. So our volume is going to equal, it starts with 265 when we're losing 11, so I'm going to do this negative 11 times the minutes, which they're going with T, not M, so negative 11 T, and we start at 265. There's our linear model, okay? And then determine the amount of water left in the tank after 15 minutes, so if we're going to do that, D part I, we're going to do volume is going to equal negative 11 times 15 plus 265, right? Negative 11 times 15 plus 265 is going to give us 100 liters. So volume at 15 minutes is 100 liters. And then the time it takes for the tank to empty. So DII is going to be, we want the volume to be 0. And then that's going to equal negative 11 T plus 265, and we're going to solve for T. So subtract 265, or you could add 11T to both sides, whichever floats your boat. 265. So this goes away. We get negative 265 equals negative 11T. Divide both sides by negative 11, and our time will be, I'm just going to do, since we got a negative over a negative, I'm just going to save some time, do 265 divided by 11. And that gives us 24.09. So we'll say 24 minutes. And just because we know how, let's turn into seconds as well. So I'm going to subtract the 24. And that gives us 0.09 of a minute. So I multiply that by 60. And that should tell us the number of seconds, which is about 24 minutes, 5 seconds. And that's roughly, so that should be little squiggle lines. Okay. Okay. Last one we're going to take a look at here is number 6. Graph alongside shows the world record times for the women's 400 meters between Marlene Matthews' record of 57 seconds on January 6, 1957, and Maria Koch's record of 47.6 on October 6, 1985. Data is modeled with this straight line graph here, where y is the time in seconds and x is the number of years since 1957. What does the model predict the time will be in 1957? So for A, we're going to go, it's going to be y equals 54.85 minus 0.2660 times x, and the number of years since 1957 would be 0, so that goes away. So that's saying that the world record in 1957, according to this graph, should have been 54.85, but it was actually 57 seconds, okay? What was the time, and why are these values different? Because you're trying to fit data that does not perfectly fit the line into a perfectly straight line, right? So this is not... all these points obviously do not make a straight line, but it's getting closer and closer as we get farther along, so that's probably why they chose this line here. Okay. Could the model be used to estimate world record times prior to 1957? Explain your answer. I mean, maybe like a year or two, but not much farther past that, because if you went much farther up here, then the times are going to get really long. So, it would take a long time to get that mile there. So this is probably only going to fit probably right in this range, because if you were to use this, just for fun, it's not asking us to, but let's just say, let's figure out what according to this, what the world record would be in 2020, let's say. So 1957. So 2020 minus 1957. That's just to make sure I don't mess this up. So 2020 minus 1957 gives us 63. So if we plug 63 into this, let's see what kind of time it's going to give us. So we got 54.85 minus 0.2660 times 63. And it says that the the world record, what is this, for the 400 meters is going to be 38 seconds. I'm going to check and see what it is right now. Hold on. Okay, so Marita Koch's record is still standing today, as I just checked here. But October 6, 1985, let's do this again. We've already finished doing this, but I just kind of want to double check our formula here just to kind of prove a point here. So if we take 1985 minus 1957, that is 28 years. So if we plug 28 into this, we get 54.85 minus 0.266 times 28, and that gives us 47.6, so that's good. Okay, but looking back to what it should be today, 38 seconds. That's a full lap around the track in 38 seconds. That's extremely fast. So obviously this would break down after probably about this 1985 point here. So it's only good. This equation here is only going to work in this short little time range for the most part. Okay? All right. That's all we have for the 4B problems. If you have any further questions, please feel free to ask in class. Thanks.